What secrets does this cosmic corpse hold? This is the Crab Nebula, the expanding cloud of debris from a star that exploded nearly 1,000 years ago. Within this beautiful chaos lies a cosmic engine of unimaginable power, and we are about to explore 50 of its most bizarre and mind-bending phenomena. You'll discover how a dead star spins 30 times every second and why it shoots out mysterious flares that defy physics. How can a cloud of gas move at half the speed of light, and what is the strange dark matter hiding in its heart? By the end of this journey, you will see the universe's most violent events in a completely new light. What do you believe is the greatest mystery waiting in the depths of space? Deep within the nebula's chaotic heart lies the source of its power, a cosmic dynamo known as the Crab Pulsar. This city-sized sphere of pure neutron star matter spins at an almost incomprehensible rate, completing a full rotation about 30 times every single second. That is faster than a helicopter blade, a dizzying spin for an object with more mass than our entire sun. This rapid rotation powers its most famous feature, acting as a cosmic lighthouse. Intense beams of radiation, channeled by unimaginably powerful magnetic fields, sweep across the sky with every turn. If our solar system were aligned with those beams, we would see a flash of light 30 times a second, a perfect metronomic pulse. The discovery of this precise rhythm in the late 1960s was a monumental moment for astronomy. It provided the first direct proof that a supernova's collapse could forge a neutron star, solving a mystery that had lingered since the original star's explosion was witnessed nearly 1,000 years ago. This tiny, spinning cinder is the furious engine that illuminates the entire nebula, a testament to the universe's ability to create order from the most violent chaos. How can something so dense spin so fast without tearing itself apart? The answer lies in the very fabric of matter itself, compressed into a state so strange it defies all earthly logic. Surrounding that furious dynamo is a storm of activity, a constantly shifting landscape of high-energy particles. These are the mysterious central wisps, ethereal structures that ripple outward from the pulsar like waves in a cosmic sea. They are not made of gas in any ordinary sense, but of electrons and positrons whipped to nearly half the speed of light by the pulsar's powerful wind. This is a velocity so extreme that a particle could travel from the Earth to the Moon in just over 2 seconds. These wisps are not static. Time-lapse observations reveal they are in constant motion, changing their shape and brightness over mere days. They brighten, they fade, and they appear to move outward in a rapid, wave-like pattern. One leading theory suggests these waves are shock fronts, similar to a sonic boom but on an interstellar scale. As the pulsar wind slams into the slower-moving gas of the inner nebula, it creates a standing shockwave. The dancing wisps we see could be the visible imprint of particles being accelerated to incredible energies at this turbulent boundary. Yet their precise behavior remains a puzzle. Why do they change so quickly? What dictates their intricate shapes? It is as if we are watching the surface of a cauldron boiling with forces we can barely comprehend. A direct visual manifestation of the pulsar's raw power reshaping its own environment in real time. This explosive energy does not stop at the nebula's glowing heart. Far beyond the pulsar and its dancing wisps lies a frontier, the nebula's outermost edge where a silent, colossal battle is taking place. This boundary is the ever-expanding shock front, a cosmic wall of force where the pulsar wind finally meets the cold, quiet emptiness of the interstellar medium. Think of it as the nebula's leading edge, a permanent wave of energy crashing into the still waters of deep space. This collision is not gentle. The material from the original explosion, still driven outward by that ancient violence and continuously energized by the pulsar's gale, is ramming into the thin gas between the stars. The force of this impact is staggering, propelling the nebula's outer shell to expand at a velocity of over 1,000 kilometers every single second. At that incredible speed, you could travel from Earth to the Moon in under 7 minutes. This relentless outward push is how we can actually witness the nebula growing. By comparing photographs taken decades apart, astronomers can measure this gradual increase in size. It is a direct visual confirmation that the Crab Nebula is not a static painting in the sky, but a living, breathing, and violently evolving entity. This measurable expansion provides us with a powerful cosmic clock. By tracing the nebula's motion backward in time, calculating how long it would have taken for all that debris to rush out from a single point, scientists can estimate the date of the original supernova. The math points to an event that occurred around 1,000 years ago, a calculation that aligns beautifully with historical records of a brilliant new star that appeared in the sky in the year 1054. This means we are not just looking at a distant cloud, we are witnessing the ongoing aftermath of a specific celestial event witnessed by our ancestors, an explosion whose light first reached Earth centuries ago and whose physical echo we can still see racing into the void today. Yet this expanding frontier is not the only place where the laws of physics are being tested. The Crab Nebula holds an even more volatile secret, one that erupts without warning. For decades, astronomers considered the crab a stable source of energy, a reliable cosmic lighthouse. That assumption was shattered when powerful space telescopes designed to see the universe's most energetic light, gamma rays, witnessed something impossible. The nebula began to produce violent, short-lived flares where its gamma-ray output would suddenly skyrocket, increasing by a factor of 5 or even 10 in a matter of hours. Think of a familiar 100-watt light bulb, steady and predictable, suddenly outshining the entire sun for a brief, brilliant moment before fading back to normal. That is the scale of these eruptions. They are not coming from the steady spin of the pulsar itself, but from some volatile region within the surrounding nebula. These flares defy our current understanding of how particles are accelerated in space. The leading theory for the nebula's glow involves particles gradually gaining speed as they surf on magnetic shockwaves, a process that cannot explain such a sudden and colossal release of energy. It suggests a completely different, unknown mechanism is at work, one that can hurl electrons to energies far beyond what any earthly particle accelerator could ever achieve. What natural process can possibly act like a cosmic slingshot, concentrating so much power into such a tiny volume of space and time? The very existence of these flares is a direct challenge, a message from the heart of the nebula that we have only begun to understand the true fury of its hidden engine. Even the most powerful flares cannot overshadow the strange, permanent structures sculpted by the pulsar's relentless wind. When we observe the Crab Nebula in the high-energy glow of X-rays, its chaotic beauty resolves into a startlingly organized shape. Two distinct features dominate the image: a brilliant, donut-shaped ring of material encircling the pulsar's middle and a powerful jet of energy shooting directly away from one of its poles. This is not random chaos. This is the hidden geometry of the pulsar's power made visible. The torus, that glowing ring, marks the equator of the pulsar's influence. Here, the pulsar wind, a hurricane of particles, flows outward at its fastest and most powerful. It is constrained into this disc-like form by the pulsar's own immense magnetic field, which acts like an invisible cage funneling the wind along a specific path. The jet, meanwhile, is a focused beam erupting from the magnetic poles, a testament to the concentrated force that cannot be contained by the equatorial ring. This entire structure acts like a colossal electrical generator. The spinning neutron star, with its unimaginably strong magnetic field, creates a powerful voltage, ripping particles apart into electrons and their antimatter counterparts, positrons, and then accelerating them to near light speed. The torus and jet are the exhaust pipes of this cosmic engine, the channels through which this focused fury escapes into the wider nebula. Why does this matter? Because this X-ray blueprint shows us that the pulsar's energy is not exploding outward in a simple sphere. It is being focused and directed with incredible precision, shaping the entire nebula from the inside out. The very form of the crab, its elongated shape and its internal ripples, is a direct consequence of this powerful directional wind. We are not just looking at an explosion's aftermath. We are seeing a complex machine in operation, one whose fundamental design is now written across the sky in the searing light of X-rays. This brilliant ring of X-ray light is more than just a beautiful structure, it is a cosmic engine of staggering power. Known as the inner ring, this feature glows with a specific type of light called synchrotron radiation. To understand this, picture an electron as a tiny, charged marble. Now imagine it is caught in an invisible, twisting maze of powerful magnetic fields, like those generated by the pulsar, and is being whipped around at nearly the speed of light. As the electron is forced to spiral along these magnetic field lines, it cannot travel in a straight line, so it must shed energy, and it does so by releasing a torrent of light. This is synchrotron radiation, the same basic process used in particle accelerators on Earth, but here it is happening on a truly astronomical scale. The entire ring is essentially a natural, celestial version of a machine like the Large Hadron Collider, but one that is vastly larger and more powerful. Within this glowing donut, electrons are being continuously accelerated to energies that our most advanced technology could never hope to achieve. They are not just moving fast, they are spiraling in a frenzied dance, and with every turn, they emit the high-energy X-ray light that makes the ring so prominent. This process is what illuminates the nebula's central machinery, turning invisible magnetic forces and unimaginable particle speeds into a brilliant, observable ring of light. It is a continuous, self-sustaining cycle. The pulsar's wind supplies the raw particles and energy, the magnetic fields confine and steer them, and the ring itself is the visible proof of their incredible acceleration. How does this cosmic accelerator maintain its perfect shape amidst the surrounding chaos? The answer lies in the delicate balance between the pulsar's outward wind and the inward pressure of the nebula's own magnetic field, a balance that creates this stable, luminous racetrack at the very heart of the storm. But this high-energy engine also flings out smaller, faster fragments of itself. Scattered throughout the nebula are strange, compact objects known as knots. These are not the gentle wisps near the pulsar, but dense, bright clumps of gas, some no larger than our entire solar system. For a long time, they were thought to be relatively stationary features frozen in the expanding cloud. Then astronomers made a startling discovery. Time-lapse observations revealed that many of these knots are not stationary at all. They are racing through the nebula at staggering speeds, some moving at over 1,500 kilometers per second. At that velocity, you could travel from the Earth to the Sun in just over a day. Their motion is not random either. They often appear to stream away from the central pulsar like sparks flung from a spinning, red-hot grindstone. Even more bizarrely, some of these knots have been seen to brighten suddenly and then fade away or even vanish entirely, all within a span of just a few years. What could possibly launch such massive blobs of material at such incredible speeds, and why would they simply wink out of existence? The leading suspect is a violent process known as magnetic reconnection. Picture the pulsar's powerful magnetic field lines as a tangled web of immensely strong, elastic bands. Sometimes these lines can snap and cross, violently rearranging themselves in an instant. This sudden reconnection releases a colossal burst of energy, similar to the process that drives solar flares on our own sun, but on a far more immense scale. It is as if a cosmic slingshot is firing, accelerating a concentrated knot of plasma to hypersonic velocities. The knot's eventual disappearance might be the moment it expands too thin to see, or when it smashes into a denser part of the nebula and dissipates its energy in a final, silent flash. These fleeting, high-speed knots are a vivid reminder that the Crab Nebula is not a serene cosmic museum piece. It is a dynamic and often violent arena where magnetic forces can suddenly concentrate their power, launching fragments of a dead star on frantic journeys through its own glowing tomb. These racing knots are just one part of a much larger, slower dance. Beyond the central chaos, the Crab Nebula reveals its true skeletal structure in the soft glow of visible light. A complex network of delicate filaments sprawls across the entire nebula, tracing the outline of the original star's shredded corpse. These are not the high-energy features near the pulsar, but the cool, ionized remains of the star itself, primarily hydrogen and helium that were violently ejected during the supernova. Their intricate, web-like patterns are not static. They are a cosmic clock ticking in slow motion. When you compare photographs of the crab taken decades apart, a remarkable story unfolds. The entire filamentary structure is expanding, its delicate threads slowly stretching and shifting over time. This is not a simple, uniform growth like an inflating balloon. Some filaments appear to brighten as they plow into other material, while others fade or change their shape entirely. Their motions provide a forensic map of the explosion's force, revealing how different layers of the star were flung outward. The vibrant colors we see in these images are not just for show, they are a direct chemical fingerprint. The reddish-orange hues come from energized hydrogen gas, while the cool blue tints indicate the presence of helium. In certain regions, you can even see the telltale green glow of doubly ionized oxygen, a sign of particularly energetic conditions. This color-coded map allows astronomers to dissect the nebula, understanding not just its structure but its composition layer by layer. Watching these filaments evolve is like watching the slow-motion replay of a cosmic detonation. They are the expanding shrapnel from a blast that occurred a millennium ago, and their continued movement is a direct, visible link to that ancient cataclysm. What new shapes will this ghostly web assume in another 100 years? But this visible light show is only part of the story. When astronomers pointed infrared telescopes at the Crab Nebula, they discovered a phenomenon that should not exist, a mysterious infrared excess. The nebula glows far more brightly in this invisible, heat-based light than anyone had predicted. This unexpected warmth is a profound puzzle because it signals the presence of something that should have been destroyed long ago: cosmic dust. These are not the dust bunnies under your bed, but tiny solid particles smaller than a wavelength of light, likely made of carbon and silicate materials. They are the basic building blocks of future planets and even life itself. The mystery is not just that this dust is there, but how it can possibly survive. The environment inside the Crab Nebula is one of the most hostile in the known universe. It is flooded with intense radiation from the pulsar and battered by a relentless wind of high-energy particles. Any dust grain forming there should be almost instantly vaporized, blasted apart by the sheer force of the energy pouring through the nebula. It is like trying to build a sandcastle in the middle of a hurricane. So how did this dust appear, and how does it endure? One compelling theory suggests this dust is a relic, a ghost from the original star. In the final, violent moments before the supernova, the star's outer layers may have cooled enough for carbon and other elements to condense directly into solid grains like soot forming in a flame. These newly forged dust particles were then flung outward in the explosion, embedded within the expanding filaments we see today. Their continued survival might be due to their location, tucked safely within the densest, coolest parts of those filaments, which act as protective shields against the nebula's raging interior radiation. Another, more astonishing possibility is that dust is continuously forming anew, right now, in these dense knots of gas, defying the odds in a constant cycle of creation and destruction. This invisible infrared glow forces us to reconsider the life cycle of stars. Even in the devastating aftermath of a supernova, in a place of pure chaos and destruction, the fundamental ingredients for new worlds are being forged and preserved. What does this hidden reservoir of dust tell us about the ability of life's raw materials to survive the universe's most violent events? This faint, sprawling halo is the nebula's ghostly echo in radio waves. While the brilliant central nebula grabs our attention in visible light and X-rays, a much larger, fainter structure envelops it completely, a vast and diffuse sphere of radio emission that stretches far beyond the familiar crab-like shape. This is the crab's radio halo, a whisper from the past that reveals the true, colossal scale of the original explosion's impact. Its origin lies with a different, older generation of electrons. The intense light show at the nebula's heart is powered by freshly accelerated particles, electrons that have just been whipped to extreme speeds by the pulsar. The halo, however, is illuminated by a more ancient population. These are electrons that were accelerated to high energies during the initial supernova blast itself 1,000 years ago and have been slowly diffusing outward ever since. They are cosmic veterans, having traveled for centuries through the nebula's tangled magnetic fields. As these older, slower-moving electrons spiral along the magnetic field lines, they emit the long wavelength radio waves that form the halo. This immense structure acts as a fossil record, preserving the history of the supernova's expansion. The halo's size and shape tell us how far the explosion's initial shockwave traveled and how it has interacted with the thin gas and dust that drifts between the stars. It marks the outermost boundary of the supernova remnant's influence, the point where the last vestiges of the star's explosive energy finally dissipate into the galactic background. Why does this ancient, fading glow matter? Because it proves the Crab Nebula is far larger than it appears. The beautiful, intricate cloud we see in photographs is merely the bright, active core of a much grander, invisible structure, a ghostly footprint left by a dying star, still visible a millennium after its light first faded from our skies. The very light that reveals the nebula's structure also encodes a hidden message about its magnetic heart. We can decode this message by studying a property of light called polarization. Think of ordinary light as a crowd of waves vibrating in every possible direction, a chaotic jumble. Polarized light, however, is different. Its waves are all aligned, vibrating in a single, orderly plane, like a crowd all marching in step. The synchrotron radiation that creates the crab's brilliant X-ray ring and central glow is naturally polarized, and the degree and angle of that alignment tell us everything about the magnetic fields that generated it. When an electron spirals around a magnetic field line, the light it emits is polarized in a direction perpendicular to that field. By carefully measuring the polarization of the light arriving from different parts of the nebula, astronomers can essentially map the invisible architecture of its magnetic fields. But this map is not a static picture, it changes. The polarization of the light we receive from the Crab Nebula's most energetic regions has been observed to vary over time, sometimes shifting over periods of just days or weeks. Why does this happen? It is a direct signature of the magnetic field's turbulent and dynamic nature. The field lines themselves are not rigid, permanent structures. They are being constantly twisted, stretched, and tangled by the violent motions within the nebula. As the pulsar wind slams into the surrounding gas, it creates a chaotic mess of currents and shocks. When a knot of plasma moves or a magnetic reconnection event occurs, it can drastically rearrange the local magnetic field geometry. This rearrangement, in turn, alters the polarization signature of the light emitted from that region. A change in the angle of polarization tells us the field lines have physically rotated. A change in the degree of polarization indicates the field has become more ordered or more chaotic. It is as if the nebula's magnetic skeleton is constantly flexing its muscles, and we are watching those subtle shifts through the filter of its own light. These time-varying measurements provide a real-time probe into the life of the magnetic field, revealing it not as a frozen framework, but as a living, breathing, and ever-evolving force that shapes the nebula's every action. What other turbulent motions might these flickering polarizations reveal as we watch this cosmic dynamo at work? The violent jet of energy erupting from the pulsar's north pole is not alone. Deep within the nebula's X-ray glow, astronomers have found tantalizing evidence for its silent partner, a faint and elusive counterjet pointing in the exact opposite direction. This ghostly feature is the missing piece of a puzzle we thought we understood. If the main jet is a focused beam of raw power, why is its southern twin so much dimmer and harder to see? The answer may lie in a cosmic game of hide and seek. The entire nebula is not a perfect vacuum. It is filled with the expanding debris of the supernova. It is possible that this southern counterjet is plowing directly into a denser, more resistant wall of this ancient stellar material. The resulting collision would rob the jet of its energy, causing it to decelerate and cool, its brilliant X-ray glow fading into near invisibility against the nebula's background chaos. Another possibility is even more fundamental. The pulsar's powerful engine itself may not be perfectly symmetrical. The process that creates these jets, likely rooted in the complex physics of the pulsar's magnetosphere, might be intrinsically unbalanced, pouring more energy and matter into one jet than the other. This would mean the very heart of the crab is lopsided, a subtle instability in its furious spin. The counterjet's intermittent visibility adds another layer of mystery. It does not always appear with the same clarity in every observation, suggesting that the conditions shaping it are dynamic, changing over time. Watching for this faint echo is like listening for a whisper in a storm, a direct probe into the hidden asymmetries and turbulent environment that govern the nebula's most powerful outflows. What other secrets about the pulsar's stability could this faint, opposing beam reveal if we could only see it clearly? This stellar detective story begins long before the explosion. The star that created the Crab Nebula was not a small, quiet star like our Sun. It was a colossal giant, a cosmic titan born in a cluster of stars we now call the Messier Open Star Cluster. By studying the motion of the nebula's remnant and tracing it backward through time, astronomers have pinpointed its likely birthplace. The progenitor star was a true behemoth, estimated to have been between 8 and 16 times more massive than our own Sun. Why is this mass range so crucial? It represents a very specific window in stellar life and death. A star with less than about 8 solar masses will end its life more quietly, puffing away its outer layers to form a planetary nebula and leaving behind a white dwarf. A star much more massive than 16 suns, perhaps 20 or more, would have met a far more dramatic fate. Its core collapse would have been so complete, so total, that not even a neutron star could withstand the force. The entire core would have continued collapsing, its gravity so immense that not even light could escape, forming a black hole. The crab's progenitor, sitting squarely in that middle ground, was perfectly poised to create what we see today. Its core was massive enough to collapse past the white dwarf stage, crushing protons and electrons together to form neutrons, but not so massive that the collapse was unstoppable. The result was this city-sized sphere of neutrons, a pulsar, the compressed heart of a giant. Its very existence tells us it was a star of a specific intermediate size. The composition of the nebula's filaments provides another clue. The abundant helium and the presence of carbon and oxygen point to a star that had progressed through the main stages of nuclear fusion in its core, burning through its hydrogen and then its helium, but it likely did not live long enough to forge heavy elements like iron in vast quantities. This star lived a fast and furious life, burning through its nuclear fuel in just a few tens of millions of years before it could no longer support its own immense weight. Its dramatic death, witnessed from Earth in 1054, was the final act in a life that was, by cosmic standards, brilliant and short. What other secrets about stellar life cycles are locked within the chemical fingerprints of this ancient explosion? The brilliant new star that blazed in the sky during the summer of 1054 was far more than a celestial curiosity. It was a global event meticulously documented by court astronomers in China and Japan, who described a guest star visible in broad daylight for 23 days and lingering in the night sky for nearly 2 years. Arabic astronomers also recorded its presence, while intriguing evidence from rock art in the American Southwest suggests Native American observers may have captured its sudden appearance on stone. This was not the birth of a star, but its spectacular death, a supernova whose light finally reached Earth after a journey of 6,500 light years. Those ancient records are not merely historical footnotes. They are a crucial piece of scientific data, providing an exact timestamp for the cataclysm that created the Crab Nebula. Knowing the precise year of the explosion allows astronomers to measure the nebula's expansion with incredible accuracy. We can calculate the exact speed of every filament and knot we see today because we know exactly how long they have been traveling. This turns the entire nebula into a calibrated laboratory. We can test our theories of stellar evolution and supernova physics against a known timeline, asking critical questions. Has the expansion been slowing down due to the resistance of interstellar material? Has the pulsar's wind been consistently energizing the nebula, or has its power fluctuated over the centuries? The answers are written in the slow, relentless movement of the filaments we observe today, a motion that began on a specific date witnessed by our ancestors. That connection transforms the crab from a distant object into a shared human experience, a cosmic event that linked cultures across the world under the same startling light. What must they have thought watching a new star outshine everything except the moon, a silent herald of a violence so vast we are still unraveling its consequences a millennium later? Even the ancient records of its brilliant light cannot account for everything the star left behind. A careful inventory of the Crab Nebula reveals a troubling discrepancy, a cosmic case of missing mass. When astronomers tally everything they can observe, the combined weight of all the visible filaments of gas, the central pulsar, and even the faint halo, the total falls significantly short of what a star of that size should have ejected. It is as if a significant portion of the original star has simply vanished without a trace. This missing mass problem forces us to question our most fundamental understanding of how these giant stars die. One compelling theory suggests the explosion itself was profoundly asymmetrical. Perhaps a great fraction of the stellar material was not blasted outward in all directions, but was instead funneled into powerful, narrow jets shooting out from the poles of the collapsing core. If we are not looking directly down the barrel of one of those jets, most of that fast-moving, dense material would have shot off into the darkness of interstellar space long ago, leaving behind only the slower, expanding shell we see today. Another possibility is that the missing mass is hiding in plain sight, but in a form we cannot easily detect. Vast amounts of cold, neutral gas, invisible to our telescopes, could be laced throughout the nebula. Or perhaps the pulsar's fierce wind has ground a portion of the debris into an ultra-diffuse fog of molecules, too faint and too cool to emit the light we typically search for. The most exotic solution points a finger at the ghostly particles known as neutrinos. In the final heartbeats of the supernova, the collapsing core releases an unimaginable flood of these nearly massless particles, which stream outward at the speed of light, carrying away a substantial fraction of the star's total energy and mass. While each neutrino has almost no mass, the sheer, staggering number of them could account for the deficit. The crab's silent gravitational pull, the subtle way its mass tugs on the surrounding space, might one day reveal the truth, telling us if the missing material is still there in some hidden form, or if it was truly lost to the void in the first violent moments of the star's death. Hidden within the colorful glow of the nebula's filaments is a subtle, high-speed dance, a phenomenon visible only when we break its light apart into a spectrum. Here, astronomers find the telltale signs of miniature bow shocks, tiny cosmic waves created when dense, fast-moving knots of gas slam into slower, surrounding material. Think of a speedboat cutting across a calm lake, its prow pushing water aside in a sharp, V-shaped wave. In the Crab Nebula, the boat is a bullet-like clump of hydrogen or helium, and the water is the nebula's own, more placid gas. The collision is so violent it compresses and heats the gas at the point of impact, causing it to glow with a very specific, shifted color. This shift is the key to the whole discovery. As the knot races toward us, the light waves from its leading edge get squeezed, shifting toward the blue end of the spectrum. The light from the gas piling up along its sides shows a different shift, revealing its sideways motion. By mapping these intricate spectral fingerprints, scientists can reconstruct the complete three-dimensional velocity of these clumps, measuring their speed and direction with stunning precision. These spectral bow shocks are more than just cosmic speedometers. Their sharpness and intensity act as a probe, revealing the density of the gas both in the bullet and in the material it is plowing through. A bright, well-defined shock wave indicates a dense knot hitting a thick, resistant medium, while a fainter, more diffuse signature suggests a lighter clump moving through a near vacuum. Each of these tiny collisions is a miniature laboratory, a fleeting experiment in hydrodynamics playing out on an interstellar scale, showing us how energy is transferred and dissipated within the nebula's tangled web. What other violent, small-scale motions might these spectral echoes be hiding, revealing a turbulence within the chaos that we are only beginning to decode? Even the nebula's ultraviolet glow refuses to stay constant. This high-energy light, more energetic than what our eyes can see, pulses and flickers in ways that defy simple explanation. The entire Crab Nebula acts like a giant ultraviolet lamp, but one with a faulty dimmer switch, its brightness changing over time. These are not the sudden, violent gamma-ray flares from the inner nebula, but slower, more subtle variations across the entire structure. The source of this ultraviolet light is the same sea of high-energy electrons that creates the X-rays and visible glow, all energized by the pulsar's relentless wind. So why would their ultraviolet output waver? One leading suspect is the pulsar wind itself. This hurricane of particles may not blow with a perfectly steady force. Perhaps the pulsar's engine experiences slight hiccups, brief fluctuations in the amount of energy it injects into the surrounding nebula. A small increase in the wind's power would send a wave of newly accelerated electrons crashing through the nebula, causing it to glow more brightly across multiple wavelengths, including the ultraviolet. A momentary lull in the wind would have the opposite effect, allowing the glow to fade slightly. Another compelling theory points to shadows moving across the cosmic stage. The nebula is filled with drifting clouds of cooler, denser gas, the very filaments we see in visible light. As these clouds move through the nebula, they can float directly between the inner ultraviolet source and our telescopes. These clouds are not transparent to ultraviolet light, they absorb it. So when a particularly dense knot of gas drifts into our line of sight, it acts like a temporary curtain, dimming the ultraviolet light we receive from the regions behind it. A few years later, as the cloud moves on, the brightness returns to normal. We are essentially watching the shifting weather patterns within the nebula, where passing storms of cold gas cast fleeting shadows in invisible light. This ultraviolet variability forces us to see the crab not as a single, monolithic object, but as a complex ecosystem of interdependent parts, where a change in the wind or a drifting cloud can alter the entire system's appearance from our distant vantage point. What other subtle rhythms might we detect if we could watch this cosmic weather for 1,000 years? Those shimmering central wisps are not static sculptures of light. They are a frenzied, living fire, a spectacle of motion you can watch unfold in real time. Time-lapse observations have captured a breathtaking truth. Over periods of just a few days, these ethereal structures surge outward, ripple, and dramatically change their shape, some even doubling in brightness before fading again. This is not a slow geological process. It is a high-speed dance driven by the pulsar's furious heartbeat. Their motion is a direct, visible link to the energetic output of the spinning neutron star. Each pulse, each release of energy from that cosmic dynamo, sends another wave of high-speed particles crashing into the surrounding medium. The wisps we see are the visible crests of these waves, the shock fronts where this relentless wind meets resistance. Watching them is like watching the surface of a pot of water just as it begins to boil, with turbulent patterns forming, merging, and vanishing in an instant. This dynamic behavior provides a rare and precious laboratory for plasma physics. Plasma, that fourth state of matter where atoms are ripped apart into a soup of charged particles, is the dominant form of visible matter in the universe, yet it is notoriously difficult to study. Here in the Crab Nebula, nature is running a continuous, colossal experiment. Scientists can observe how magnetic fields confine and accelerate plasma, how shock waves propagate through it, and how energy is transferred on an astronomical scale. The rapid changes in the wisps tell us that the conditions at the nebula's heart are far from equilibrium, a constant state of violent adjustment. What triggers a particular wisp to brighten so suddenly? Is it a surge from the pulsar or the collapse of a magnetic structure? Each flicker and shift is a piece of a puzzle, helping us understand the fundamental physics that governs not just this nebula, but the behavior of matter and energy throughout the cosmos. Yet for all its particle-accelerating fury, the Crab Nebula holds a profound silence. It should be a roaring source of neutrinos, the ghostly subatomic particles that are the unmistakable signature of the most violent events in the universe. The nebula's intense radiation and powerful magnetic fields are constantly smashing protons and other atomic nuclei together, a process that should create a shower of these elusive particles. Yet when scientists point their most sensitive detectors toward the crab, they hear almost nothing. This neutrino non-detection is a baffling quiet that speaks volumes. It challenges our fundamental understanding of how cosmic rays, those high-energy particles racing through space, are born and interact within such chaotic environments. Think of the nebula as a colossal factory. We can see the raw materials going in, we can witness the immense energy powering the machinery, and we can observe the brilliant light shining from its windows. But we cannot hear the expected roar of its engines. This silence forces a difficult question. Are the protons, the primary fuel for neutrino production, simply not present in the amounts we assume? Perhaps the crab's accelerator is overwhelmingly efficient at hurling electrons to fantastic speeds, but is surprisingly poor at accelerating the heavier protons. Without a sufficient population of high-energy protons colliding with other matter, the factory cannot produce its expected neutrino output. Another possibility is even more intriguing. The nebula's magnetic fields may be acting like a perfect containment system, trapping protons within its glowing interior for millennia. These trapped particles would continue to spiral along the magnetic field lines, never gaining enough escape velocity to collide with the denser gas needed to create neutrinos. They are prisoners of the very forces that give the nebula its shape, their potential for creation locked away. This profound quiet from the crab is a crucial clue. It suggests that not all cosmic accelerators operate by the same rules, and that the pathways to creating the universe's most energetic particles are far more diverse and mysterious than we ever imagined. What other cosmic factories are humming along silently, their true engines hidden from our view? That profound silence is broken by a different kind of signal, one that twists and turns on its long journey to Earth. The radio waves streaming from the Crab Nebula carry a hidden imprint, a subtle rotation encoded within their very vibration. This is the Faraday rotation effect, a cosmic clue that allows us to see the invisible. When polarized radio waves travel through a region filled with charged particles and magnetic fields, their plane of polarization slowly twists like a dial being turned. The amount of this rotation depends on two key ingredients: the strength of the magnetic field along our line of sight and the density of the electrons the waves encounter. It is a direct measurement of the magnetic environment the waves had to navigate. By carefully measuring how much the polarization angle of the crab's radio emission changes at different frequencies, astronomers can perform a kind of three-dimensional magnetic tomography. Lower-frequency radio waves are more easily twisted than higher-frequency ones, and this difference creates a unique fingerprint for every pocket of space within the nebula. It is as if each cloud of magnetized plasma leaves its own signature twist on the radio signal, a signature we can decode. When scientists map these Faraday rotations across the entire Crab Nebula, they do not find a simple, orderly magnetic field neatly aligned from one side to the other. Instead, the map reveals a turbulent and deeply tangled mess. The field lines are twisted into knots, braided into complex ropes, and folded back on themselves in a chaotic whirl. This three-dimensional map shows us that the magnetic field is not a passive scaffold. It is an active, dynamic participant in the nebula's chaos. The constant push of the pulsar wind, the collisions of high-speed knots, and the sheer violence of the ongoing expansion are all working together to stir the nebula's magnetic heart into a frenzy. This Faraday rotation map is our best evidence that the crab's magnetic skeleton is alive, a constantly shifting web of force that guides the nebula's evolution and contains the secrets of its most powerful eruptions. What other turbulent motions are recorded in these twisted radio whispers, and what do they tell us about the ultimate fate of this magnetic maelstrom? The nebula's glowing edge is not a perfect, smooth sphere. Along its outer rim, you can see strange, dark indentations like deep bays cutting into a coastline of light. These shadowy inlets are not empty voids, but regions where the nebula's brilliant expansion has been halted. They are the imprint of a silent, cosmic collision. For centuries, the crab has been racing outward, its shock front plowing through the thin gas between the stars. But space is not a perfect vacuum. It is scattered with cold, dense clouds of molecular gas and dust, the leftover raw materials from the births of other stars long ago. When the nebula's advancing wall of energy slams into one of these pre-existing clouds, it cannot simply sweep it aside. The dense cloud acts like a celestial breakwater, resisting the onslaught and forcing the expanding gas to flow around it. The result is a dark bay, a pocket of shadow where the glowing, energized filaments of the crab are pushed back, unable to penetrate the cold, stubborn obstacle. These dark features are more than just sculpted shapes. They are active sites of compression and heating, even if they appear dark to our eyes. The collision between the nebula and the cloud is likely triggering new waves of star formation deep within the cloud itself, a second-generation birth catalyzed by the death of a star. The nebula's beautiful and complex shape is not just a product of its internal violence. It is a portrait of its interaction with the wider galaxy, a permanent record of its journey through a clumpy and unpredictable interstellar medium. What other invisible structures might be hiding just beyond the light, their presence only revealed by the way they bend and shape this cosmic storm? At the most extreme end of the electromagnetic spectrum, the Crab Nebula reveals yet another layer of its power. Its hard X-ray emission consists of photons carrying immense energy, far beyond what standard hospital X-rays produce. To generate this specific type of light, electrons must be accelerated to almost unbelievable velocities, reaching energies that dwarf the capabilities of the most advanced particle colliders on Earth. The sheer intensity of this hard X-ray glow points to a cosmic accelerator of breathtaking efficiency, one that operates continuously within the nebula's heart. How can this natural machine possibly work so well? The leading theory, known as diffusive shock acceleration, describes a process where particles crisscross a magnetic shockwave repeatedly, gaining a little more speed with each pass. It is like a ball being bounced between two converging walls, each collision propelling it faster. Yet, even this robust model struggles to account for the crab's extreme output. The theoretical maximum energy a particle can gain from this process, known as the radiation reaction limit, is being approached, if not outright broken, within the nebula. This suggests there is another, far more potent mechanism at work, one we have not yet identified. Some physicists speculate that magnetic reconnection events, those violent rearrangements of field lines, could be acting as ultra-powerful slingshots, catapulting electrons to these phenomenal energies in a single, explosive instant. The persistent glow of hard X-rays is a constant, silent challenge to our understanding of plasma physics, forcing us to ask what fundamental processes we are still missing in this chaotic and magnificent cosmic laboratory. Even the furious dynamo at the nebula's heart is not a stationary anchor. The Crab Pulsar itself is on the move, racing through the void at a staggering speed of over 100,000 kilometers per hour. This is not the gentle drift of a star in its galactic orbit, but a high-velocity escape, a direct result of the violence that created it. Astronomers measure this movement, known as proper motion, by precisely tracking the pulsar's position against the background of more distant stars over many years, watching its slow but relentless trek across the sky. This incredible velocity is the smoking gun for a profoundly lopsided explosion. When the star's core collapsed, the supernova was not a perfectly symmetrical blast. Imagine a firecracker with slightly more gunpowder packed on one side. When it detonates, the casing would be kicked in the opposite direction. The supernova is thought to have worked in a similar, though vastly more powerful, way. Intense jets of neutrinos or sloshing matter may have erupted from one side of the collapsing core in its final milliseconds, rocketing the newly born neutron star away like a cosmic cannonball. This natal kick has profound implications for all neutron stars. It explains why we find so many of these dense stellar corpses far from the crowded star clusters where they were likely born. They are the celestial shrapnel from ancient explosions, sent careening across the galaxy on lonely journeys that last for billions of years. The Crab Pulsar's specific trajectory, when traced backward, helps confirm its origin in that specific star cluster, linking its high-speed flight directly to the chaotic dynamics of its own violent birth. How many other stellar ghosts are racing through the darkness, forever exiled from their birthplaces by the asymmetric kick of a supernova? These vibrant filaments are a chemical tapestry woven from the corpse of a dead star. As we map their intricate colors, a clear and puzzling pattern emerges. The distribution of elements is far from uniform. Some filaments glow with the deep red of hydrogen, the universe's most basic building block. Others shine with the cool blue of helium, while a few reveal the brilliant green of oxygen. This is not a random splatter of stellar guts. It is a forensic snapshot of the star's final moments. Each element tells a story of its origin deep within the progenitor star. The abundant hydrogen likely came from the star's vast outer envelope, the first layer to be blasted away. The helium and oxygen we see were forged in the star's fiery core, under immense pressure and temperature over millions of years. The very fact that we see these core elements mixed together with the outer hydrogen is a crucial clue. It tells us that the supernova explosion was not a simple, orderly peeling away of layers. Instead, it was a violently chaotic event. Intense instabilities during the collapse must have sent powerful ripples through the dying star, churning its interior like a blender. This process, known as explosive mixing, flung deep-seated heavy elements outward while dragging lighter hydrogen inward, creating the chemically scrambled masterpiece we see today. Why is one filament rich in oxygen while its neighbor is mostly helium? The answer is locked in the specific turbulence of that single, world-ending detonation, a mixing process we are only now beginning to understand through the silent language of light and color. Beyond the fury of its X-rays, the Crab Nebula unleashes an even more potent form of light. Ground-based telescopes designed to see the universe's most energetic photons, with names like Veritas and ESS, have detected a persistent glow of very high-energy gamma rays emanating from the nebula. These are not ordinary gamma rays. Each one carries 1 trillion electron volts of energy, a level of power denoted by the term TV, placing them among the most energetic photons we can observe in the entire cosmos. To put that immense energy into perspective, a single one of these gamma-ray photons packs over 1 trillion times more energy than a particle of visible light. The mechanism that creates this phenomenal light is a cosmic game of pool played at near light speed, a process known as inverse Compton scattering. Imagine one of the nebula's ultra-relativistic electrons already traveling at a fantastic velocity, colliding with a much lower energy photon, like a particle of starlight or the faint glow of the cosmic microwave background. In the collision, the tiny electron, possessing immense kinetic energy from its speed, transfers a huge amount of that energy to the photon. It is like a massive, high-speed billiard ball striking a nearly stationary one, sending the lighter particle flying with unbelievable force. The previously meek photon is suddenly transformed, boosted into the stratosphere of the electromagnetic spectrum to become a devastatingly powerful TV gamma ray. This process reveals something profound about the nebula's interior. The very presence of these gamma rays is direct evidence that the crab is filled with electrons of almost unimaginable energy. For an electron to boost a photon to a TV, it must itself be far more energetic, pushing the very limits of what our theories say is possible in such an environment. The fact that this TV glow is steady, unlike the violent flares seen at slightly lower energies, suggests that this incredible particle acceleration is a continuous, fundamental process within the nebula's chaotic heart. It means the crab is not just a temporary factory for high-energy particles, but a permanent and supremely efficient cosmic accelerator, whose most powerful products announce their existence in flashes of light that can tear apart atoms in our own atmosphere. What other unfathomable energies are being generated in this storm, hidden from our view except for these fleeting trillion-volt whispers? Even the pulsar's steady radio beat is capable of sudden, explosive fits. On rare occasions, the Crab Pulsar's regular rhythm is shattered by a giant pulse, a burst of radio waves so intense it can be millions of times brighter than its normal emission. These are not the gradual brightenings of the surrounding wisps, but a direct and violent scream from the pulsar itself, lasting mere millionths of a second. The true magic, however, happens after that initial scream fades. For a brief moment, the sheer power of a giant pulse does not just travel out into space. It slams into the surrounding nebula like a tidal wave of pure energy, exciting the sea of electrons that fills the void around the pulsar. This sudden, violent injection of energy forces those electrons to radiate that power away, creating a temporary afterglow that can be seen at other wavelengths, particularly in visible light. It is as if a flash of lightning, the giant pulse, strikes a vast, invisible cloud of gas, making the entire cloud fluoresce for an instant before fading back to darkness. This phenomenon provides a direct and immediate link between the pulsar's most erratic behavior and the nebula it illuminates. We are witnessing a chain reaction of energy transfer in real time, a cosmic cue ball where a flicker from the central dynamo causes the entire surrounding table to briefly light up. What other fleeting connections between the pulsar and its nebula might these brilliant split-second flashes reveal? Its own magnetic fury does not exist in a vacuum. The Crab Nebula's powerful, self-generated field is expanding directly into the Milky Way's own pervasive magnetic tapestry, a subtle but constant force that permeates the space between the stars. This is a clash of cosmic magnets, a silent interaction happening at the very frontier of the nebula. The galaxy's magnetic field is incredibly weak by comparison, a faint whisper against the nebula's roar, but it is everywhere, a structured background against which the crab is pushing. This interaction may be subtly shaping the nebula's outermost layers, guiding the flow of its expanding particles like a riverbank channels water. You would not expect a raging river to change course because of a single blade of grass on its bank, but when that river meets the persistent, gentle slope of a valley, its path is inevitably directed. The galactic magnetic field is that valley, an immense, gentle slope on an interstellar scale. As the nebula's own tangled magnetic field balloons outward, it must push against this galactic framework. The field lines from the crab likely compress and drape themselves over this larger structure, potentially explaining slight asymmetries in the nebula's faint radio halo or influencing the direction of the fastest particles escaping its grasp. Could this galactic pressure be one reason the nebula appears slightly elongated in one direction, its shape molded not just by internal violence but by the gentle external hand of the galaxy itself? This subtle interplay reminds us that no cosmic object, no matter how powerful, is truly an island. It is connected to the galaxy in ways we are only beginning to sense, its final form written by both its own explosive past and the silent magnetic currents of its home. This broad spectrum of light, from radio whispers to gamma-ray screams, is not a featureless slope. Etched into its profile is a crucial landmark, a subtle bend known to astrophysicists as the cooling break. It is the point where the power of the nebula's light begins to drop off more steeply, a kink in the curve that tells a powerful story about the life and death of its most energetic electrons. Think of the electrons as tiny cosmic batteries, storing the immense energy given to them by the pulsar's wind. As they spiral through the magnetic fields, they spend that energy, emitting synchrotron radiation across the entire spectrum. An electron with a lot of energy emits high-energy light like X-rays and gamma rays. An electron with less energy emits lower-energy light like radio waves. The cooling break marks the specific energy where an electron's life changes dramatically. Below this energy, an electron can spiral for a very long time, emitting radio waves for centuries before it loses a significant amount of its power. But above the cooling break, an electron's life is brutally short. It radiates away its immense energy in X-rays and gamma rays so efficiently that it effectively burns out in a matter of just a few years. The location of this cooling break in the spectrum is a direct measurement of the strength of the nebula's magnetic field. A stronger magnetic field forces the electrons to spiral more tightly, making them radiate their energy away even faster and shifting the cooling break to a lower energy. By precisely measuring where this bend occurs, scientists can effectively take the temperature of the nebula's magnetic heart, calculating its average strength without ever touching it. This single, subtle feature in the crab's grand light show is a fundamental diagnostic tool, a natural gauge that reveals the balance between how quickly the pulsar injects new energy and how quickly the nebula's own magnetic forces cause that energy to dissipate into the void. What other hidden signatures of this cosmic energy balance are written into the nebula's brilliant, multicolored glow? The faintest whispers of light can travel for millennia. Scattered across the vast space between us and the Crab Nebula are clouds of interstellar dust, and some astronomers believe these cosmic way stations hold a delayed recording of the original explosion. This is the phenomenon of a historical light echo, a chance to witness the supernova of 1054 with 21st century eyes. When the star detonated, its light exploded outward in a brilliant, expanding sphere. Most of that light traveled directly to Earth, arriving in the year 1054, but a tiny fraction of that initial flash did not take a straight path. It struck these distant, unseen dust clouds, bouncing off them like a voice echoing in a cavern, and was sent on a new, longer journey to our planet. That scattered light is only now arriving, nearly 1,000 years later. The challenge is immense. This echo is incredibly faint, a ghostly signature superimposed on the much brighter, constant glow of the nebula itself. Detecting it requires comparing meticulous photographs taken years or even decades apart, searching for subtle, expanding rings of light centered on the nebula that should not be there. A confirmed light echo would be a scientific treasure beyond price. It would allow us to perform spectroscopy on the light from the actual explosion, analyzing its chemical composition in a way the ancient astronomers never could. We could determine the star's temperature in its final moments and measure the precise velocities of its ejected material, all from an event whose direct light faded from the sky centuries ago. It would be like finding a pristine audio recording of a legendary speech, allowing us to analyze nuances our ancestors could only describe in words. What other secrets might be hidden in that delayed flash, waiting for the right technology to tease them out from the darkness? Its own heartbeat is slowly fading. The Crab Pulsar, that furious cosmic dynamo, is gradually winding down, its spin losing energy with every passing year. Precise timing of its radio pulses allows astronomers to measure this slowdown with incredible accuracy, calculating a specific value known as the breaking index. In a perfect, simplified universe, a spinning neutron star behaving like a pure magnetic dipole, a sort of celestial bar magnet, should have a breaking index of exactly 3. But the Crab Pulsar stubbornly refuses to comply. Its measured value is consistently lower, hovering around 2.5. This small numerical discrepancy is a colossal clue. It tells us that the simple model is incomplete, that our understanding of this cosmic engine is missing some crucial pieces. The pulsar is not just a spinning magnet in empty space. It is coupled to its environment in complex ways. One possibility is that some of its rotational energy is being sapped by a process far more subtle than pure magnetic radiation. The powerful pulsar wind, that relentless hurricane of particles, carries away a significant amount of angular momentum. Think of an ice skater spinning with their arms outstretched. If they begin to throw handfuls of sand away from their body, each tiny grain carries away a minuscule amount of spin, causing the skater to slow down faster than expected. The pulsar wind is that constant stream of sand, an additional braking mechanism beyond the basic magnetic model. Another theory points to the interior of the neutron star itself. Its crust of iron might be floating on a bizarre quantum fluid of superfluid neutrons. Friction between this superfluid and the solid crust, or tiny starquakes that suddenly change the star's shape, could also be altering the rate at which the spin decays. The breaking index problem is a profound reminder that this city-sized object is not a simple top. It is a deeply complex physical system. Its slow, measured deceleration, a coded message about the turbulent physics churning within its core and the intricate ways it shares its power with the storm it created. What other hidden processes are stealing its spin, and what do they reveal about the true nature of matter under such impossible pressure? Scattered among the crimson glow of hydrogen are brilliant, sapphire blue filaments that shine with the unmistakable light of helium. These are not mere accents in the nebula's tapestry. They are the preserved ashes of the star's long-vanished central fires. Helium is the fundamental product of hydrogen fusion, the residue left over after a star has spent billions of years burning its primary fuel in its core. Finding it now concentrated in specific, isolated filaments tells a dramatic story of the star's final moments. It reveals that these regions were once part of the star's deep interior, layers that should have remained hidden beneath a heavy blanket of hydrogen. Their presence so far out in the expanding debris is evidence of a profound stellar evisceration. During the supernova, titanic forces must have ripped through the star's structure, violently dredging up these inner layers of helium and hurling them outward into space. The chaotic distribution suggests the explosion was not a clean, orderly unraveling, but a deeply messy and turbulent event. It is as if the star's guts were churned by a cosmic blender, with deep-seated helium from the core becoming intimately mixed with the outer hydrogen envelope in the frenzy of the detonation. Why do some filaments remain so purely helium-rich while others are a scrambled mix? The answer lies in the unique physics of the explosion, where powerful shock waves and instabilities fragmented the star, preserving pockets of its original layered composition even as the overall structure was torn asunder. These brilliant blue veins are the fossilized remnants of the star's fiery heart, now forever frozen in the expanding shell of its own destruction. What other secrets about the final convulsions of a giant star are locked within the chemical purity of these ancient stellar ashes? Even the nebula's own radio voice can be muffled by its internal fog. At the very lowest frequencies of radio light, the crab's expected brilliant glow begins to fade, absorbed before it can even escape into space. This is not an effect of distant dust clouds, but a case of self-absorption, where the nebula's own cooler, slower-moving electrons get in the way of the light generated by their faster, hotter siblings. Picture a crowded concert hall where the music from the stage is so loud that the people in the back cannot hear it because the sound is absorbed and scattered by the mass of bodies in front of them. In the nebula, the low-frequency radio waves act like that deep, resonant music. They are trying to travel through a thick fog of relatively cool electrons, and these electrons are so numerous that they effectively soak up the radiation, preventing it from reaching our telescopes. This strange dimming is far more than a simple obstruction. It is a crucial diagnostic tool, a window into the nebula's hidden population of low-energy particles. By precisely measuring at which frequency this absorption kicks in and how strong it is, astronomers can perform a cosmic census. They can calculate the density and temperature of this vast sea of slower electrons that would otherwise be completely invisible to us. This reveals that the crab is not just a factory for the most extreme particles, but also a reservoir for a much more numerous, quieter population, the foundational sea of particles from which the most energetic ones are selected and accelerated. Why does this cooler, denser population exist, and what role does it play in the nebula's overall energy balance? This faint absorption at the lowest frequencies reminds us that for every spectacular, high-energy event, there is a much broader, quieter reality, a hidden structure that supports the entire brilliant and chaotic system. This spinning dynamo might not be as alone as it seems. A fascinating theory suggests that in the immediate, chaotic aftermath of the supernova, not all of the star's debris was flung outward. Some of it, perhaps drawn by the newborn pulsar's immense gravity, may have fallen back, settling into a vast, thin disk of gas and dust swirling around the central star. This hypothetical structure is known as a fallback disk, a cosmic whisper of a past that was almost erased. Think of it as the ghost of the explosion's first moments, a relic of the initial chaos that could still be shaping the nebula today. Such a disk would be incredibly faint and difficult to detect, hidden in the brilliant glare of the pulsar and its surrounding storm. Its presence would solve several lingering puzzles. For instance, it could provide a source of additional material that the pulsar's fierce wind continuously slams into, helping to shape and energize the inner ring of X-rays we observe. More subtly, it could act as a brake on the pulsar's spin. The friction of this disk, however tenuous, rubbing against the pulsar's magnetic field could be siphoning away rotational energy, contributing to that mysterious braking index that has always been slightly off. This would mean the pulsar is not just slowing down from its own magnetic power and wind, but is also being gently held back by the faint, dusty remains of its parent star. The very existence of such a disk challenges our image of a clean, complete explosion. It paints a picture of a more complex death, where some material escapes at incredible speeds while other fragments are pulled back by gravity's unforgiving hand, forever bound to the stellar corpse they once nourished. How many other pulsars are secretly accompanied by these phantom disks, their silent presence dictating the rhythm of a cosmic heartbeat? the nebula's glowing filaments are not uniformly bright from core to edge. Each one possesses a strange kind of celestial sunburn, a brilliant and searingly hot outer layer that sharply contrasts with its cooler, darker interior. This is the skin effect, a direct and brutal consequence of living next to a cosmic fury. The surfaces of these filaments are the parts directly exposed to the pulsar's relentless barrage of ultraviolet and X-ray radiation. It is like the difference between standing in the gentle warmth of a sunlit room and pressing your hand directly against a white-hot branding iron. The outside of the filament is that branding iron, heated to extreme temperatures by the pulsar's direct glare, causing it to glow with an intense, sharp light. The interior of the filament, however, is partially shielded. Its own density acts as a form of protection, absorbing the most damaging radiation in its outer skin and leaving the core to exist in a relatively cooler, calmer state. This creates a luminous shell, a thin and brilliant skin that outlines every twist and turn of the gaseous structure. When we look at these filaments, we are not seeing a solid tube of light. We are seeing a hollow cylinder, a cosmic neon sign where only the outer surface is fully ignited. This effect provides a crucial clue about the density and structure of the filaments themselves. A thick, dense filament would show a very pronounced skin effect with a bright rim and a very dark center. A thinner, more diffuse filament might be almost entirely skin, glowing more uniformly throughout. By measuring the contrast between the bright edges and the dimmer cores, astronomers can effectively weigh these cosmic tendrils, determining how much material is packed into each one and how well it can shield its own heart from the storm. Why do some filaments have such a crisp, bright shell while others appear more diffuse? The answer is written in their unique densities, a silent testament to the chaotic forces that sculpted them during the explosion and which now dictate how they face the ongoing fury of their creator. This particle wind is not a smooth, uniform gale. The hurricane of matter flowing from the pulsar is fundamentally bumpy and uneven, a phenomenon known as an anisotropic wind. We tend to picture this wind as a perfect sphere of energy expanding outward, but the reality is far more textured and chaotic. Imagine a lawn sprinkler that does not spray water in a steady, symmetrical pattern, but instead has several powerful, erratic jets that pulse and change direction. The pulsar's wind behaves in a similar fashion, with intense, concentrated streams of particles erupting from its surface at varying intensities. This inherent lumpiness in the wind's very structure provides a compelling explanation for many of the nebula's persistent mysteries. Why does one side of the inner ring appear brighter than the other? A stronger wind stream could be slamming into that specific part of the nebula, energizing it more than its surroundings. Why do the central wisps flicker and surge with such unpredictable timing? They could be responding to individual gusts and lulls in this anisotropic flow, brightening when a dense clot of particles hits the shock front and fading when a momentary void passes through. This uneven wind acts like a sculptor's chisel with a wobbly hand, creating the asymmetrical shapes and the constant, small-scale variability we observe throughout the nebula. It suggests the source of this chaos is not just in the nebula's turbulent environment, but originates deep within the pulsar's own engine. The process that rips particles from the neutron star's surface and accelerates them into space may itself be subject to violent, small-scale instabilities. Perhaps the magnetic field at the surface is not a perfect dipole, but is tangled into localized knots that act as powerful nozzles. Or maybe the process of pair production where particles are born is inherently clumpy. This anisotropic wind model transforms our view of the entire system. The Crab Nebula is not a simple, symmetrical bubble being inflated by a steady breath. It is a complex, living structure being molded and shaken by a storm that is itself fundamentally imperfect and unpredictable. What other subtle asymmetries in the nebula's form might be the permanent signature of a wind that has never blown evenly? This magnetic chaos has a specific and explosive name: magnetic reconnection. It is the universe's ultimate short circuit, a process where the invisible architecture of magnetic fields suddenly and violently rearranges itself. Picture the Crab Nebula's magnetic field as a vast, tangled web of immensely strong, elastic bands. These field lines are not static. They are constantly being twisted and stretched by the pulsar's wind and the turbulent motions of the plasma. Sometimes field lines pointing in opposite directions are forced together. They cannot simply pass through one another. Instead, they snap, breaking like overstretched rubber bands, and then reconnect into a new, lower energy configuration. This sudden snapping and relinking releases a colossal burst of energy all at once. It is like a cosmic slingshot being released, channeling the power stored in the twisted magnetic fields directly into the surrounding soup of particles. This single, explosive event can heat the local plasma to incredible temperatures, and most importantly, it can hurl electrons and positrons to nearly the speed of light in a fraction of a second. This process is a prime suspect for explaining the nebula's most violent tantrums. Those sudden, powerful gamma-ray flares that defy explanation could be the direct result of a massive magnetic reconnection event near the pulsar. In an instant, a vast reservoir of magnetic energy is converted into particle motion, creating a brilliant flash that outshines the entire nebula. But reconnection is not just for dramatic flares. It might also be the hidden engine behind the constant, high-energy glow. Throughout the nebula, countless smaller reconnection events could be continuously pumping energy into the particle population, acting like a distributed network of tiny accelerators. This would explain how the nebula maintains its furious output and how those high-speed knots of gas are launched on their frantic journeys. Magnetic reconnection transforms our view of the nebula's magnetic field. It is not just a confining cage or a guiding hand. It is a dynamic and volatile fuel source, a store of potential energy that can be tapped in sudden, violent bursts, reminding us that the true power of the crab often lies in the silent, building tension of its own invisible forces. Long before the final cataclysm, the star was already shedding its skin into the void. Its final millennia were marked by a relentless stellar wind, a steady gale of particles flowing from its surface that carved out a vast cavity in the surrounding interstellar space. When the supernova finally came, its blast wave did not expand into a uniform medium. It erupted into this pre-shaped bubble, this ghostly echo of the star's earlier life. Today, the outermost structure of the Crab Nebula might still bear the imprint of that ancient wind, a fossilized footprint of the star's final breaths. The expanding shell of debris is not just plowing through random space, it is likely interacting with the delicate, ionized relic of that pre-supernova outflow. This interaction could explain subtle asymmetries in the nebula's faint outer halo, or why certain filaments appear to be piling up against an invisible wall. It is as if the explosion is chasing the shadow of its former self, a cosmic chase scene frozen in time. The progenitor star, in its dying days, was essentially preparing its own grave, sculpting the very arena where its remnants would continue to evolve for millennia. How much of the nebula's present form was dictated not by the violence of its death, but by the persistent, gentle pressure of its final years? This ghostly wind reminds us that a star's death is not a single event, but a long process where the actions of its late life set the stage for the drama of its end. Even the pulsar's perfect rhythm holds a hidden irregularity. Its spin is not a flawless cosmic metronome. Astronomers have detected tiny, unpredictable hiccups in its rotation known as glitches, sudden speed-ups where the pulsar's spin rate increases by a minuscule but measurable amount in an instant. Imagine a perfectly tuned watch suddenly gaining a few seconds for no reason, then continuing to tick at its new, slightly faster pace. That is what a glitch is for the Crab Pulsar. These events are followed by a gradual relaxation period where the spin slowly decays back toward its pre-glitch trend over weeks or months. Alongside these distinct events is a more constant, jittery background known as timing noise, a persistent shakiness in the pulse arrival times that makes long-term predictions of its spin subtly uncertain. The source of this stellar unsteadiness lies deep within the neutron star's impossible interior. One compelling explanation points to starquakes. The pulsar's solid iron crust, under unimaginable strain from its rapid spin and powerful magnetic fields, can occasionally fracture and readjust, much like tectonic plates on Earth. A sudden crustal shift, a starquake, can make the entire star contract slightly. Just as a spinning ice skater pulls their arms in to spin faster, this minuscule contraction of the neutron star causes its rotation to speed up instantly, creating a glitch. Another, more exotic theory involves the star's quantum heart. Beneath the solid crust, the core is thought to be a superfluid, a bizarre state of matter that flows without any friction whatsoever. This superfluid is weakly coupled to the solid crust. Normally, it spins at the same rate, but as the crust gradually slows down due to its magnetic braking, the frictionless superfluid can lag behind, storing rotational energy like a wound-up spring. Suddenly, this superfluid can transfer its pent-up spin back to the crust in a violent surge, kicking the star's rotation faster in a glitch. These internal convulsions are more than just a curiosity. They directly impact the nebula we see. A glitch represents a sudden release of the pulsar's internal energy. This extra jolt of power can ripple outward through the pulsar wind, potentially causing a corresponding brightening or restructuring of the central wisps and the inner ring. The pulsar's hidden tantrums send waves through the storm it commands, a direct link between the secret life of a neutron star and the brilliant chaos of its expanding tomb. What other invisible shifts within this cosmic dynamo are subtly reshaping the nebula's furious heart? This rapid-fire strobe effect from the pulsar does more than mark time. It acts as a cosmic flashbulb, and the surrounding nebula is a vast, three-dimensional cathedral waiting to be illuminated. Every time one of the pulsar's intense flashes of light, particularly in ultraviolet and optical wavelengths, erupts outward, it lights up a different cross-section of the surrounding gas. Because the nebula is not a flat painting but a deep, complex structure, the light from each flash takes a slightly different amount of time to reach various filaments and wisps. A knot of gas that is closer to us will be lit up almost instantly by the pulse, while a similar knot located directly behind it from our perspective will be illuminated a few days or weeks later, once the light has had time to travel the extra distance. The result is a moving wave of light, an echo that appears to travel through the nebula over time. It is like watching lightning illuminate different parts of a massive, distant thunderhead, revealing its depth and hidden contours with every flash. By meticulously tracking these echoes, astronomers can perform a kind of celestial triangulation. They know the exact time the flash left the pulsar, and they measure the precise delay before a specific filament lights up. Since they also know the speed of light is constant, that delay directly translates into a physical distance. A 1-week delay means that particular filament is about 1 light week farther away from the pulsar than a filament that lit up immediately. Piece by piece, echo by echo, scientists can build a precise 3-dimensional map of the nebula's entire inner structure, turning a beautiful 2-dimensional image into a quantifiable, depth-filled model. This technique reveals which filaments are actually in front of others, how the gas is distributed along our line of sight, and the true, contorted shape of the voids and cavities within the storm. What other hidden chambers and tunnels might these fleeting echoes reveal within this labyrinth of light? That powerful wind from the pulsar is actively rewriting the standard rules of a supernova's afterlife. In a typical stellar explosion, the physics are governed by 2 distinct shock waves. The forward shock is the one we can see, the expanding wall of debris that plows into interstellar space. But there should also be a reverse shock, a wave that travels back inward toward the center of the blast, like an echo rebounding through the expanding cloud of stellar guts. This reverse shock is crucial. It heats the inner debris, making it glow brightly in specific wavelengths of light and serving as a key diagnostic tool for understanding the explosion's energy. Yet when astronomers search for this signature in the Crab Nebula, they find it is strangely weak, almost absent. It is as if the echo never formed or was silenced before it could reverberate. The prime suspect for this cosmic silencing is the relentless gale from the Crab Pulsar. In a normal supernova remnant, the center is a quiet, empty cavity. The reverse shock can form and travel freely through this void, but the Crab's center is not empty or quiet. It is filled with a hurricane of high-energy particles, a pulsar wind that is constantly pushing outward with immense pressure. This wind acts like a powerful fan blowing against a door, preventing it from swinging inward. The reverse shock wave is that door, and the pulsar wind is holding it shut. The energy flooding out from the spinning neutron star is so intense that it completely overwhelms the conditions needed for a reverse shock to develop and propagate. Instead of a wave traveling back toward the center, the pulsar wind creates a standing shock front, a permanent, stable boundary where its own fury meets the expanding shell. This boundary is the source of the brilliant X-ray ring and the dancing wisps, a permanent feature that has replaced the temporary, inward-moving shock that would exist in a quieter remnant. This missing reverse shock is more than just a curious omission. It is direct evidence of how a central engine can hijack a supernova remnant, reshaping its entire evolution and overriding the standard post-explosion script. What other fundamental rules of stellar death are being broken by the sheer power of this single, spinning cinder? Deep within the churning heart of this cosmic storm, matter itself is being forged into its own mirror image. The Crab Nebula is a confirmed factory for positrons, the antimatter twins of electrons. These are not exotic theoretical particles. They are being produced in vast quantities right now, born from the nebula's most violent processes. Whenever a high-energy gamma-ray photon, itself a product of the nebula's furious particle accelerator, collides with another photon or a magnetic field, it can spontaneously transform. In a process known as pair production, the photon's immense energy condenses into two new particles, an electron and its antimatter counterpart, a positron. They are created together, a matched set of matter and antimatter appearing from pure energy. This continuous cycle is fundamental to the nebula's existence. The pulsar's wind is rich with these particle pairs, and their endless creation and annihilation helps fuel the entire system's brilliant glow. But these positrons are not all doomed to immediately vanish. Many are caught by the turbulent magnetic fields and accelerated to nearly the speed of light, joining the sea of high-energy particles that fill the nebula. Some of these antimatter particles, however, manage to escape the Crab's chaotic grasp. Once free, they become part of the diffuse background of cosmic rays that constantly bombard our galaxy. This means the Crab Nebula is actively seeding the Milky Way with antimatter. While each positron is incredibly tiny, the nebula's immense output over thousands of years contributes a significant trickle to this mysterious cosmic ray background. When one of these positrons eventually encounters a normal electron in the void between stars, they annihilate each other in a final, silent flash of gamma rays, their existence ending as it began in a burst of pure energy. How many other stellar remnants are quietly contributing their own antimatter to this invisible, galaxy-wide drizzle? Even the nebula's most brilliant X-ray structures refuse to stay still. The Chandra X-ray Observatory has captured a startling truth over its decades of observation. The inner ring and jet, those powerful symbols of the pulsar's focused energy, are not permanent fixtures. Their brightness and shape change over the course of years, a slow but undeniable pulse that reveals the long-term moods of the central engine. This is not the frantic flicker of the gamma-ray flares or the rapid dance of the central wisps. This is a deeper, slower rhythm, a year-scale variability that shows the pulsar's influence on its surroundings is anything but constant. 1 year, the eastern side of the glowing ring might appear brighter and more sharply defined. A few years later, that same region has faded, while the jet streaming from the pole has thickened and intensified. These changes are a direct echo of the pulsar's own activity. Think of the pulsar wind not as a steady breeze, but as a variable gale. When the wind intensifies, it sends a stronger wave of particles slamming into the inner ring, causing that entire structure to glow more fiercely in X-rays. A temporary lull in the wind's power would allow the ring to dim slightly as the supply of fresh, high-energy particles temporarily dwindles. The shifting structures also act like a cosmic windsock, showing us the direction and focus of this powerful gale. If the jet brightens and becomes more collimated, it suggests the pulsar's magnetic funnel is focusing the outflow with greater precision. If the ring appears lopsided, it tells us the wind itself is blowing more strongly from one part of the pulsar's equator than the other. These year-to-year transformations prove that the relationship between the pulsar and its nebula is a dynamic conversation, not a monologue. The nebula's form responds directly to the commands of its hidden heart, its brilliant X-ray light tracing the slow, powerful heartbeat of a cosmic giant. What other subtle, long-term shifts might we witness if we could watch this celestial clock for another century? The very heart of the crab is spinning on a tilted axis, a cosmic wobble that shapes its entire storm. The pulsar's physical spin axis, the orientation of its powerful magnetic poles, and even the direction it is flying through space are all pointed in different directions. This fundamental misalignment turns the pulsar into a wildly unstable gyroscope, and its chaotic influence radiates outward into the nebula. Imagine a lighthouse where the lamp is not only spinning rapidly, but is also bolted to the wall at a strange angle, while the entire building is sliding sideways across the rocks. The light beam would sweep across the sky in a wildly complex pattern, never repeating the same path twice. This is the reality within the crab. The pulsar's magnetic axis, from which its powerful wind and twin jets erupt, is not lined up with its rotational equator. This misalignment is the primary reason we see its lighthouse beam pulse at all. If the magnetic poles were perfectly aligned with the spin axis, the beam would always point in the same direction, and we would never see its flash. The fact that we see a pulse means we are watching that misaligned beam sweep across our line of sight 30 times a second, but the complexity does not end there. The entire system is also in motion, with the pulsar racing through the nebula it created. This direction of travel is its own third independent vector, a line of flight that adds another layer of asymmetry to the already turbulent mix. How does this three-way misalignment manifest in the nebula we see? It directly explains the lopsided appearance of the inner X-ray ring and the inconsistent strength of the polar jets. The pulsar's wind does not blow with uniform force from all points on its surface. Because the magnetic axis is tilted, the wind is strongest and most focused from the magnetic poles and equator, creating an anisotropic or uneven gale that constantly batters the surrounding nebula from a shifting set of angles. This ever-changing push is what sculpts the central wisps into their frenzied dance and causes one side of the nebula to appear brighter and more energized than the other. The entire structure is not a symmetrical bubble. It is a constantly evolving sculpture, its form dictated by the unstable, wobbling heart of a spinning giant whose own internal compasses can never agree. Yet even this hidden reservoir of warm dust is not the final piece of the puzzle. The nebula's faint whispers extend into the realm of submillimeter radio waves, revealing a ghostly population of even colder dust grains, frigid structures existing just a few degrees above absolute zero. These are not the particles glowing in the infrared, but something far more difficult to detect, an almost invisible frost clinging to the nebula's darkest corners. Finding such profoundly cold material inside a raging inferno seems impossible. The environment should be far too violent, the radiation far too intense for any solid object to remain so deeply frozen. Their existence suggests these grains are incredibly well shielded, perhaps buried deep within the densest, most opaque cores of the nebula's filamentary knots, where the pulsar's fierce glare cannot reach. This cold dust component is more than a mere curiosity. It could be a significant contributor to the nebula's lingering mystery of missing mass. These frigid grains, collectively, could represent a substantial amount of material that has simply been too cold and too dark for our telescopes to see, silently adding their weight to the nebula's total. Their presence also provides a stunning clue about the supernova's own chaotic chemistry. For dust this cold to form, the ejecta from the explosion must have cooled with astonishing rapidity, allowing carbon and silicates to condense directly out of the expanding gas like snowflakes forming in a suddenly chilled cloud. This challenges our understanding of these cosmic blasts, suggesting that pockets of the ejected material can cool and settle into solid form even while surrounded by the continuing violence of the pulsar wind. How much of the original star was transformed into this dark, cold ash? And what does its survival tell us about the resilience of matter in the face of total stellar destruction? For decades, the Crab Nebula served as a celestial lighthouse for high-energy astronomers, a steady beacon in the tumultuous cosmos. Its unwavering glow in X-rays and gamma rays made it the perfect cosmic reference point, a standard candle against which all other violent objects could be measured. Scientists would point their new telescopes at the crab first, using its predictable, well-mapped flux to calibrate their instruments with absolute precision. It was the gold standard, the one constant in a universe of variables, allowing researchers to be certain that a flicker from a distant quasar or a flare from a black hole was real and not just an artifact of their equipment. This reliability transformed the crab from an object of study into a fundamental tool, the bedrock upon which our understanding of the high-energy universe was built. But this foundational role is now facing a profound challenge. The very flares and variability that make the nebula so fascinating are undermining its status as a stable ruler. How can you trust a measuring stick that keeps changing its own length? When the nebula's gamma-ray output suddenly quintuples in a matter of hours, that carefully calibrated scale is thrown into chaos. An instrument tuned to the crab's normal state would be completely blinded by such an eruption, its readings rendered useless for comparing any other object. This has created a quiet crisis in high-energy astrophysics. The community is now grappling with a difficult question. Can the Crab Nebula still be trusted as the universe's premier standard candle, or have its own violent tantrums forced us to seek a new, more placid cornerstone for our cosmic measurements? The search is on for a calmer, more predictable source, but nothing else in the sky offers the same brilliant, well-studied consistency across such a broad range of energies. The crab's rebellion forces a humbling realization. Even our most trusted guides in the cosmos are capable of unexpected change, reminding us that the universe refuses to be pinned down by our need for order. This very stability we once relied upon forces a deeper, more unsettling question. Could the furious engine at the heart of the Crab Nebula ever produce something far more catastrophic than a flare? Is it possible, however remote, that this system could one day generate a short gamma-ray burst? These are the most violent explosions in the universe since the Big Bang. Events that can release more energy in 2 seconds than our Sun will emit across its entire 10-billion-year lifetime. The conditions required for such a cataclysm are almost unimaginably extreme. They typically involve the merger of 2 neutron stars or the collapse of a massive star into a black hole, scenarios that forge jets of material moving at over 99.9% of the speed of light. The Crab Pulsar is a single neutron star, and while it is energetic, it is not on the verge of collapse. It spins fast, but not nearly fast enough to tear itself apart through centrifugal force. Its magnetic field, while powerful, is orders of magnitude weaker than the hypermagnetic monsters thought to power true gamma-ray bursts. So, the simple, reassuring answer is no, the Crab Nebula is not a likely candidate for such an event. Its violence is contained, a continuous storm rather than a single, final detonation. Yet, the nebula constantly reminds us of the gaps in our understanding. Those mysterious gamma-ray flares, which appear to defy the radiation reaction limit, demonstrate that an unknown, explosive acceleration mechanism is already at work. Could a perfect storm of internal instabilities, a massive starquake, a colossal magnetic reconnection event, or a sudden, total failure of its superfluid interior, somehow chain together into a single, runaway reaction? It is a thought experiment that pushes at the boundaries of physics, a reminder that we are still learning what matter is truly capable of under such impossible stress. The crab's greatest lesson may be that we should never become too comfortable with our cosmic neighbors, for even the most familiar and seemingly stable objects can harbor the potential for profound and terrifying surprise. The Crab Nebula is more than a spectacle of light. It is a natural engine for the universe's most powerful projectiles. This celestial storm actively contributes to the galactic sea of cosmic rays, a relentless rain of high-energy atomic nuclei that constantly bombard our planet. We are all immersed in this invisible drizzle right now, with thousands of these particles passing through our bodies every second. While most cosmic rays come from distant, unknown sources, the crab provides a nearby, observable laboratory to see how they are born. The process begins deep within the nebula's chaotic heart. Electrons are whipped to near light speed by the pulsar's wind and magnetic fields, but protons and heavier atomic nuclei are also caught in this acceleration frenzy. These larger particles, the building blocks of atoms, are far more massive and carry immense energy when launched into space. When one of these high-energy protons escapes the nebula's tangled magnetic grasp, it becomes a genuine cosmic ray, a solitary traveler on an epic journey across the galaxy. Studying the crab's unique light signature allows us to trace this process. The nebula's gamma-ray glow, especially during its violent flares, acts as a fingerprint for proton collisions. When a high-energy proton smashes into a slower-moving atom of gas within the nebula, the impact creates a shower of secondary particles and a distinctive flash of gamma-ray light. By detecting this specific type of emission, astronomers have indirect proof that protons are being accelerated to cosmic ray energies inside the crab. This helps solve a century-old mystery, providing a clear, local example of how at least some of the galactic cosmic rays are forged. It demonstrates that supernova remnants like the crab are likely one of the primary factories for these elusive particles, continuously seeding the galaxy with the high-energy shrapnel of dead stars. How many other cosmic rays racing past us right now began their existence in a similar, long-vanished stellar explosion? Even this stellar wreckage can cast a shadow across the entire cosmos. Scientists have used the Crab Nebula's brilliant X-ray glow to see a silhouette against the oldest light in the universe, the cosmic microwave background. This faint afterglow from the Big Bang fills all of space, a nearly uniform sea of microwave radiation. To study its most subtle properties, astronomers needed a perfect, distant light source to shine through it, and they found one in the crab. Think of it like holding your hand up to a bright, evenly lit wall. You do not see the details of the wall itself until your hand blocks the light, revealing the wall's true texture and brightness by contrast. The Crab Nebula acts as that cosmic hand. Its powerful, steady emission in X-rays serves as the backlight. As these X-rays travel for thousands of years across space, they pass through the cosmic microwave background on their way to our telescopes. The nebula is so bright and its X-ray spectrum so well understood that any slight dip or distortion in that expected signal can be measured with incredible precision. This dip is the shadow, a tiny absorption feature caused by the crab's X-rays interacting with the primordial microwaves. the depth and shape of this shadow are not random. They directly reveal the intrinsic temperature and density of the cosmic microwave background along that specific line of sight. It is a direct measurement, a calibration against the universe's most fundamental backdrop. This sophisticated trick turns a nearby cosmic catastrophe into a scientific tool, a precise ruler for measuring the universe's deepest past. What other ancient secrets might we uncover by using the universe's own violent events as our lanterns to illuminate the dark? This brilliant light show is not a permanent fixture of the cosmos. Over the span of a human lifetime, the Crab Nebula has been slowly, imperceptibly dimming. Historical measurements comparing photographic plates from the early 20th century with modern digital images confirm a subtle but steady decline in its overall optical brightness. The nebula is fading, not with a dramatic flicker, but with the deep, slow breath of a cosmic giant settling into old age. This gradual dimming is a direct consequence of its relentless expansion. As the nebula grows, the same amount of light-producing material is spread across an ever-increasing volume of space. It is like a drop of ink in a glass of water, brilliant and concentrated at first, but becoming fainter and more diffuse as it spreads out. At the same time, the nebula is cooling. The furious, high-energy particles that were initially accelerated by the pulsar are slowly losing their energy, radiating it away as light over centuries. As they cool, they emit less of the brilliant visible light we see, shifting their output to longer, less energetic wavelengths. This long-term fading provides a crucial timeline for the nebula's life cycle. It allows us to project its future, to see the day, millions of years from now, when its glorious filaments will have expanded into near invisibility, their glow completely diluted by the vastness of space. The light that captivated our ancestors will one day fade to a cosmic memory, a final, quiet whisper from a storm that once ruled the sky. The glorious storm we see today is a fleeting moment in a cosmic story spanning billions of years. The Crab Nebula's expansion will not slow for eons, its delicate filaments stretching ever outward into the void. As it grows, its beautiful chaos will dilute, the vibrant colors of ionized gas fading first to a pale, uniform glow and then to near invisibility against the blackness of space. The intricate tapestry of knots and wisps will dissipate, their material scattering into the interstellar medium, becoming one with the raw stuff from which new stars will one day be born. This is not an end, but a transformation, the final act of returning a star's substance to the galaxy. Meanwhile, the furious heart of this storm, the Crab Pulsar, is living on borrowed time. Its incredible spin is a finite resource, relentlessly being converted into the light and wind that power the nebula. Over millions of years, its rotation will slow from 30 times a second to once a minute, then once an hour, and finally to a barely perceptible turn. The metronomic pulse that once defined it will falter and fall silent. No longer a lighthouse, it will become a dark, cold sphere of neutrons, its internal fires long since extinguished. This stellar corpse will continue its lonely journey, a fossil from a forgotten explosion, drifting through the galactic void for timeframes longer than the current age of the universe. Its final destiny is to become a cold, black diamond in the darkness, a monument to a cataclysm whose light faded eons ago. What legacy does such a violent death ultimately leave? It seeds the galaxy with the elements for new worlds and perhaps for new life, ensuring that even in its final fading, the Crab Nebula gives birth to futures we can scarcely imagine. From its spinning heart to its fading outer glow, the Crab Nebula reveals a universe of relentless change and violent beauty. We have journeyed past a pulsar spinning faster than a helicopter blade, through dancing wisps that ripple at half the speed of light, and into the silent mystery of its missing mass. We have witnessed sudden flares that outshine the sun and traced the paths of high-speed knots racing from a furious magnetic slingshot. This is more than a cloud of cosmic debris. It is a living laboratory, a place where the fundamental laws of physics are tested daily, where matter is forged into antimatter, and where magnetic fields twist into explosive knots. Every strange phenomenon, from the ghostly counter-jet to the cold dust that should not exist, is a piece of a puzzle we are still assembling. The crab's story is unfinished, its greatest secret still locked within its chaotic light. Which of its 50 strange wonders captured your imagination the most? Was it the unpredictable tantrums of its gamma-ray flares, or the silent, steady expansion of its ancient filaments? Share your thoughts in the comments below, and if you are hungry for more journeys into the unknown, be sure to subscribe for our next deep dive into the universe's most enduring mysteries.